Hi, in this video, I want to convince you to never use one at a time experimental designs. Okay, so in experimental designs, we have a bunch of different choices for our situation. We can use Latin squares, partial factorial analysis, full factorial analysis. Um, we can do ad hoc. Well, one that's very common that I've come across that's very easy for people to understand is one at a time experimental designs. One at a time experimental designs are where we set a baseline for our independent variables. And then one at a time, we change an independent variable value. And so what ends up happening is that every single run of my experiment, everything is baseline except one independent variable on each trial. Okay, well, why would we do this? Well, this feels like this is going to be very easy to understand. This feels like it's going to give a very good estimate of main effects, but in fact, it's not living up to the hype. It's not going to deliver. There are better ways, and as statisticians, we are going to deliver those better ways. The other designs that you see in textbooks, all of them will do better than one at a time experiment, or maybe not all of them, but almost all of them will do better than one at a time experiments. All right, so let's dig into this. So one at a time experimental designs are very easy to understand. We set a baseline for all of our independent variables, and on each trial, only one variable has a non-baseline value. This way, it's very easy to connect to, hey, what's going on in this experiment? I've only got one variable that's varying, so it's easier to figure out what's happening and to interpret the individual trials. And this feels like this would deliver a lot for us because this is easy to understand. But when we get into the linear algebra of regression, we're going to find, hey, this isn't going to deliver. All right, so because one variable is different than baseline, it's super, super easy for our stakeholders and ourselves to know what's happening on each individual trial. Um, and people intuitively believe that this is going to do a good job of detecting main effects. Unfortunately, it's not going to. Uh, this is inferior to other approaches, and in fact, other approaches actually detect main effects better, but those other techniques are going to be a little bit harder to understand in terms of the individual trial independent variable values. And so we need to judge what's going on and do what's best for our project. So you heard me say, do not use one at a time experimental designs. One thing I've learned is every time a professor tells you never, ever, ever, ever do something in statistics, there is a really good time that you are going to have to do that as an actual working data scientist. That number one reason is that my stakeholders want it this way. My number one goal when I work is to deliver value to my stakeholders. If this is how my stakeholders want it and I can't convince them otherwise, this is how I'm going to deliver it. Poor data science and weak data science is better than no data science. We have to make sure that our stakeholders will accept our results. That's our number one priority when we do things. Yes, I could do a better job lots of times, but if my stakeholders don't understand what's going on, they're going to be more likely to back off and not trust the results, not use my work. So there is a time and a place for everything that your statistics professor tells you to never, ever do. All right, so when should we use one at a time experimental designs? First and foremost, if I am desperately short on data, I only have a few trials I can execute because of time, money, budget, whatever, and I have the number of trials I have is less than or equal to the number of main effects. Well, you know what? This might be a good choice for me to try and just pick up something out of the data. Partial factorial designs would it probably give me a more complete situation, but this is a good way to go. If I'm woefully short on trials and data. Another situation where this isn't that bad is if I know a priori that interactions are non-existent or so small that they're negligible and I can just ignore them. If I'm in that situation, one at a time experimental designs are going to be all right because the shortcomings aren't going to come to bear as much. And ultimately, the main reason why I would ever do something against my statistics professors when I'm doing work is that my stakeholders want it that way. So if my stakeholders want simpler experiments so that they feel comfortable with what's going on, so that they accept my work, that's how I'm going to do it. All right, so let's get going. First thing I'm going to do is I'm going to set up my workspace like I do in every one of these videos. First, I pull in the piping function. So Magrittr, some artwork going on in there. And I like to set my options to just 2 digits. So that way I don't get blasted in the face by a bunch of numbers. I avoid scientific notation for my interpretation ease. And I just clear my workspace of anything that might already be there to make make sure I don't have any bugs or any artifacts floating around. Okay, so let's build some experimental designs for us to compare to see what's going on so that we can understand this. So I'm not going to do like a full rigorous proof on this, but you could definitely generalize this, and you could definitely do pencil and paper mathematics to extend the arguments that I show you to a theoretical setting. All right, so what I'm going to do, I'm going to use plus or minus 1 to represent high and low levels of my independent variables. Why am I doing it this way? Well, remember from like the partial factorial and full factorial videos is that the plus or minus 1 are going to set me up so I have orthogonal matrices when I do full factorial. All right, so what I'm doing there is I'm making sure that I don't have any correlation between my predictor variables when I full factorial, partial factorial. Now, this is just a coding. And a result from theoretical linear regression is that I can center and scale my predictor variables any way I want, as long as that I maintain positive variance on the values. I can center and scale any way I want, and I'm not going to actually change the accuracy of my models. The coefficients will change and the intercepts can change, but the actual accuracy is not going to change. And since this is experimental design discussion, I can pick any value I want that's convenient for me. I'm going plus or minus 1. So the plus 1, what we're doing is we're saying, hey, I'm going to take a very high but reasonable value for my independent variable. When it's negative 1, I'm going to take a low but reasonable value for my independent variable. Why are we doing this? Well, remember, if I'm doing a linear regression model, I'm making the assumption that I have a straight line situation. Or if I have a straight line situation, I only need 2 points to draw a line, right? Well, what I'm doing, I'm extending this idea to data so that I just go high and low. I'll show at the very end of the video that this is a good idea to get more accuracy out of your coefficient estimates. All right. All right, so I'm building out some experimental designs to show you. I'm going to say that -1 corresponds to the baseline level for all variables. So here, what I'm saying is that -1, -1, -1, -1, all independent variables, -1 represents my baseline level for my experiment in my one at a time experimental design. All right, so I'm going to build 2 experimental designs right now. First one is going to be one at a time, and we're going to have 9 trials here. And I'm going to have 3 main effects, and each variable is going to deviate from baseline 3 times. So I have 3 main effects, and they're going to be -1 6 times each over all the experiments, and +1 3 times. Now here I'm going to use my 3 main effects, and I'm going to do 8 trials of full factorial. So here, each variable is going to be baseline half the time and non-baseline half the time. Okay, so let's go ahead and generate our design. All right, so here, this is my one at a time matrix. And you can see that I've got the intercept as a constant. Then first main effect, I'm going, so the first main effect is the first 3 rows are not baseline. And then the middle 3 rows are going to be not baseline on the second main effect. And then the last three rows are going to be not baseline for the third main effect. Okay, so look down, see every time I have a positive one that's not baseline, negative one is baseline in how I'm constructing this. And then B, boom, we have the positives in the middle. C, we have positives at the end. And then I have my interaction columns. So this way I can understand what's going on. Now, I want to point out something to you right here, right now. Look at the intercept column. Look at the ABC column. They're both constant ones. This is why this is an inferior method. Notice that the intercept and the highest interaction are perfectly correlated with each other. Okay, well, what about A with BC? Well, look at this. Always positive first three, always positive first three. Always negative after that, always negative after that. If I take B and compare it to AC, I see the same phenomenon. If I compare C to AB, and this is the easiest one to see, look at this. Same values every single time. This is not a coincidence. All right, so we can see that A is perfectly correlated with BC, B is perfectly correlated with AC, C is perfectly correlated with AB. Okay, so right off the bat, I hope I've convinced you that we are not going to get maximum information out of our experiments. Now, people could say, well, I want repeated iterations to get a better estimate of the coefficients. And intuitively, that makes a lot of sense because here I've got 3 times with this I'll have 3 observations going on, doing the same thing repeatedly, 3 observations and 3 observations. And you could reasonably believe that you would get a better result, but you actually won't. Believe it or not, I'll show you that at the very, very end. Now let's look at the full factorial design. All right, full factorial design. You'll notice that A is half the time positive, half the time negative. B is half the time positive, half the time negative. C is half the time positive, half the time negative. And then the same thing for all of the non-intercept columns. Half the time they're positive, half the time they're negative. Okay? And the intercept is just the constant ones, which, that's not that interesting. So this represents the values that I would put in my experiment as I control the values of A, B, and C to see what happens with my dependent variable Y. Okay, so now let's check the span of the 2 experiments. All right, so even though the 1 at a time experiment has more trials, remember that one had 9 and full factorial has 8. So I've put more time, money, and effort into 1 at a time experiments, but it's actually going to be inferior from a span point of view. All right, so when I look at 1 at a time experimental design and I look at the reduced row echelon form, you'll notice I have a bunch of zeros here. All the zeros. I actually have a span of 3. Really? Okay, so in a higher dimensional sense, my 1 at a time experiment in higher dimensional space is actually a 3-dimensional plane instead of a higher dimensional full span linear algebra system. And so I'm coming up short. I can't fulfill the full potential of my data by doing this. We will be losing information. So I won't be able to pick up all aspects. And so, I'll be at most, I'll be able to get 3 coefficients to be, or sorry, 3 parameters, intercept and coefficients to be estimated. Now let's look at the reduced row echelon form of the full factorial. Well, look at this. This is the perfect identity matrix. This is an 8x8 identity matrix. This means that I have full rank, I have full span, I have everything that I want here. So in the 8-dimensional space of what's going on, I can reach any point in that space. Here I have to get lucky and have what I want be on that 1-dimensional plane, or sorry, 2-dimensional plane in higher dimensional space. Sorry, three-dimensional subspace. It's a 3-dimensional subspace. I misspoke. All right, so now let's take a look at the correlation. All right, so like I said before, one at a time design has duplicate columns. The intercept is equal to the three-way interaction. A is equal to two-way interaction of B and C. B is equal to the two-way interaction of A and C is equal to the two-way interaction of A and B. You'll notice that whichever letter is missing, it's equal to every single time. That's not a coincidence. All right, so it is impossible for one at a time experiments to distinguish between the intercept and the highest order interactions and main effects and the highest -1 interaction levels. Okay, so like we can just see right there that there is a hard upper limit on what I can get out of these experiments. All right, now if I had more main effects, fewer main effects, I'm going to have perfect either equality or perfect correlation 100% of the time. And of course, equality is perfect correlation also. And because of that, it doesn't matter what I do. If I only use one at a time experiments, I cannot get a full understanding of my data or of the situation using the data from these experiments. Also, to make this even worse, one at a time experiments have non-zero correlation between main effects, making it harder to interpret what's going on. So remember, from a linear algebra point of view, I want perpendicular orthogonal main effects. And what that does for me is that I know that I can isolate what's going on with each of those main effects. So I have an easier interpretation. I don't have to worry about correlation aspect at all. So check this out. All right, so when I look here, so this is a correlation of my one at a time. I have one on the diagonal. That is normal. That I will always have one on the diagonal of a correlation matrix. That's all right. But notice I've got a one on the skew diagonal going up the other direction. Okay, so that means that that the A column is perfectly correlated with the BC column, which means I have redundancy in what's going on. That means I can't, I can't get full representation. I see that the B column is perfectly correlated with AC. I see that the C column is perfectly correlated with AB. All right, so that's not ideal. But also, A and B have a negative 0.5 correlation. A and C have a negative 0.5 correlation. You notice that all of these are non-zero values. And if I was to have done a full factorial design, these would have actually have been all zeros and making my situation better. All right, so let me show you the picture. All right, so what I want to see 0 for correlations between distinct columns. So if I see two different columns, I always want perfect 0 correlation. Now, the question mark on the intercept is going to come up because the intercept is constant, it has 0 variance, and so correlation doesn't make sense when I have 0 variance because of the division by the standard deviation or the sum of squares difference from the means. And so, I can just see that it's not that good. Now, if I was to go to the diagonal matrix that I have here, the correlation matrix is a perfect diagonal matrix except for the intercept, which correlation doesn't make sense, which is fine. I see when I look here, boom, look at that. I have 0 correlation between distinct columns, which means that this is going to be very easy to interpret what's happening. All right, so now let's kick it up a notch. Let me prove to you that even if I go with 4 variables for a one at a time experiment, 16 trials, I get the same results effectively. And let's run through this. So I'm going to go through. I've got A, B, C, and D now. I'm creating all of my two-way interactions, all of my three-way interactions, and my four-way interaction. And here I'm doing this to say that I'm doing repeated iteration. So so at this point, I have an experimental design of one trial for each distinct independent variable values, but I want to do each of them 4 times. And so I'm going to go through and, just rbind to do that. Okay. So now, once again, we see that we have a low rank system. So at most, I can estimate 4 parameters. Look at the correlation plot, and I see the same effects. It's a little bit more interesting to look at now because now I have a positive and negative aspect. All right, so I've got perfect correlation along the diagonal because it's equality with itself, and then I have perfect negative correlation going in the other direction. So if I take A and look at the interaction with everything but A, I see perfect negative correlation. If I look at B and the interaction with everything but B, I see perfect negative correlation. If I look at C and compare that to the interaction with everything but C, I see, perfect correlation, and I can just keep on going down the line and seeing this. And also, I have correlations between all of the different columns, except for when I get down in like, towards the middle here. But you see, I have all of these, connect 4 looking dots going on for plus or minus 0.5 correlations. So I don't have that great situation. If I would have done full factorial, I would have had 0 correlations everywhere, but where the diagonal gives me 1 every single time. Okay, so now I want to convince you that 1 at a time experiments do not detect main effect as well as other designs. All right, so when I've encountered this, the idea, and I've actually encountered this from a professor who was supposed to be very, very strong in statistics, not an actual statistician, computer science background, who made exactly this claim. And so I want to debunk this. Very common mistake, easy to believe this, but I'm going to show you we can do better. The other arguments I've given you show that we can do better with other experimental designs, but I want to go a little bit further and debunk the claim that we'll get better estimate of main effects. 1 at a time experiments do not detect main effects as well as other designs. To provide evidence for this, let's look at the variance of simple linear regression and the intercept. All right, so in simple linear regression, the variance of the slope is expressed with this equation. Now, notice what I've got. I've got a hard fixed value. So this sigma squared comes from the situation that I'm trying to estimate. I have no control over what's going on. This is a hard, firm value, and it is what it is. Whatever it is, that's what it is. I can't change it. I have to work with it. But I have control of the x values. Okay, so let's look at this denominator. X minus x bar and then I square it and I add it up. Doesn't that look a lot like the variance of x? Yes, it does. Yes, it does. Okay, so if I, now depending on which formula for variance estimate you want to use, I could, multiply the top and bottom by -1 or sorry, n-1 or n to, get the s of x. But the punchline there is if I increase the variance of x, I decrease the variance of the slope estimate. Increase the variance of x, I decrease the variance of slope estimate. Now, another interesting thing is you don't see n in there, huh? Kind of an interesting phenomenon that we don't see in. What will happen is if I get more and more data points, then adding more terms in there is actually going to increase the denominator. And by increasing the denominator, I'm going to be shrinking the variance along the way. So larger sample size is going to help me, but the n is not like explicitly stated as you intuitively would have expected, or at least I would have expected when I learned this. All right, so what I want to do, I want to pick the x values that maximize the variance. Well, it works out that if I have, let's say I have a bounded range for my values of x, then in that situation, I want half at the maximum, half at the minimum. That will give me maximum variance on x. Very simple proof if you want to, go and do that. Like it's pencil and paper, super easy. I will get the most bang for my buck, assuming that linear regression is the best model for it, not lowest curve or generalized added model or anything like that. But if I believe that simple linear regression or multiple linear regression is the right way to go, I want extreme values of x and nothing in the middle. Remember, if I want to draw a straight line, I need 2 points. That's like an elementary school fact. What I'm doing here is, since I have data, I'm putting all my data points out at the extremes to kind of improve the overall straight line estimation. Okay, and so we can see now that taking the x values and putting them as far away from each other at 2 separate points, as far away from the middle as I can, is going to improve the estimate of the slope. Well, let's take a look at the variance of the intercept. All right, so here we can see explicitly that the larger sample size is going to improve the performance of this. This will, if I get a large sample size, this is going to shrink down pretty nicely. Now here we have this ratio, and you can see overall by increasing the variance, I'm going to be decreasing the variance of the intercept. Now this x bar squared, now I might be able to get a better estimate by being a little bit more nuanced in it, but usually we don't pay as much attention to the intercept. Usually when I'm doing hypothesis testing, I'm way more focused on the slope. And so because of that, the slope is the better way to go. One at a time experiments isn't really going to address this all that well. So in general, a wider spread of x is going to actually do better for both the slope and the intercept. There are some cases where the square of x bar, I might be able to improve this fraction overall, but most of the time, the simplest way to think of it is maximize the variance. I'm going to improve what's going on. Now, other experimental designs are going to use a 50-50 of high and low values, Latin squares, partial factorial, full factorial. Of the independent variables. This will lead to greater variance and better coefficient estimation. All right, so now what I'm going to do, I'm going to show you the variance of the design of experiment matrices. And you can see that in this one, in my one at a time experiments, each main effect column has a variance of 1. Okay. Well, what is it for full factorial? Well, full factorial, I can see that it's a little bit bigger. All right, so since it's bigger, that shows, hey, I would get a better estimate using the full factorial way. Now here, it's not a big difference, but there is a difference. And since there is a difference and I can control the situation, that's the whole point of experimental design. I'm going in and I control what values of x to set up. I want to pick the values of x in my experiment that gives me the best results possible. Boom, I know which way to go. All right, well, that's all I've got for you. Life is short. Do math.